materials. So here's the deal with composite materials. We're going to get somehow the best of both worlds. That's what we're trying to do with a composite. And so another way to think about it is if we have a certain properties of one materials class and certain properties of another materials class, and we're trying to combine them in such a way. Now, we don't really get the best of both worlds. That's kind of what we're thinking. We end up somewhere in between. Okay, so is a polymer composite as stiff as the carbon fibers we're reinforcing it with? No, but it is processable, because polymers are very processable, and it is very lightweight. So we'll talk about this. We end up somewhere in the middle with some combination of properties. We're going to look at the properties of our composite, and they're going to depend, just like with everything else we've talked about, on what they're made up of, what are the properties of the different constituents, and how are they distributed, what's their macro, not so much microstructure now, but macrostructure. And that's how, ultimately, this is the taxonomy, or how we talk about polymers. What's their matrix, what's their reinforcement, and how is that reinforcement? So a carbon fiber reinforced polymer. Okay, so you look at this point, you should be able to fill out this yourself. And so this slide right here is a really good studying tool for, say, the final exam, or really anything. For metals, what are their pros? They're conductive. They have a great balance of strength and ductility. They're very tough. Sometimes we want the magnetic aspect. We'll get to that. But the cons, why don't we want to use steel for everything?
Heavy.
It's heavy. It's very dense, right? They can orient in those really high atomic packing factor. The highest packing, the most dense packing of spheres you can get is HCP or FCC. They have low creep resistance, and they're not very corrosion resistant. They want to go back to the ore they started from. Same thing with ceramics. What do we like about ceramics? They're stiff. They're insulating. They're very creep resistant, and they're light. A lot of them, especially the covalently bonded ceramics, are light, low density. But you can't use them in tension, and they're difficult to form. Polymers are lightweight, cheap, easy to form, but they're not that strong. So we combine some of these. So we'll take the things that we like about a polymer, and we'll fix the things that are wrong with it. So a good way to think about this is, in general, the primary role of the reinforcement is to fix what the matrix is lacking in. Okay, so when you look at polymers, why don't we reinforce polymers with metals? Well, what we like about the polymers is that they're lightweight and easy to machine. But metals are dense. That's not fixing that. What we need is higher stiffness and strength. So usually we're reinforcing polymers with glass or carbon fibers, or aramid fibers, which is another type of polymer. But like Kevlar, it's technically a polymer, but in a fiber setting, it's like ridiculously strong, like a ceramic. If we have a metal matrix, what would we want to reinforce it with? We want to fix creep and corrosion and density. So we're going to go with something less dense, like a ceramic, that's more creep resistant, like a ceramic, and the corrosion resistant we're going to fix by coating it with a ceramic or a polymer, so paint. If we have a ceramic matrix composite, how do we fix the toughness? That one's a little weird. You fix it by adding in ceramics, which is really cool. We're going to see that, but not till Friday. Okay, so we've talked about this idea before. So these are not composites. Composites have to be two chemically dissimilar things. Okay? So, but we have seen that, like, if we look here at this is a hyper-eutectoid steel, which means that since we have pro-eutectoid cementite, to D. We have a composition between 0.67 and 2.14. So we're forming cementite first. So for this steel, we have a hard phase and a soft phase. Which is the hard phase? The cementite. What's the soft? Ferrous. We've got hard and soft, kind of like carbon fiber in a polymer matrix. So we have different phases with different properties. It's still not a composite, but that's one of the things that made steel so great, is that we had one phase to give us ductility and one phase to give us hardness and strength. Okay. With the polymers, we saw the same thing with these polycrystalline polymers. We had the crystalline regions to realign, to give us strength and stiffness, and the amorphous regions to give us ductility because of the chain untangling and retangling. So two different parts of the microstructure had two different properties, and they came together to give us an aggregate, overall, kind of stiff and kind of ductile. Very ductile and kind of stiff. Okay, so we've seen this idea before. Two different parts of the microstructure giving us two different properties. But now we're talking about it on a slightly more, a different size scale, so more of a macrostructure. So composites have to be chemically dissimilar. So when we talk about composites, you don't need to know this graph, but basically, the one thing I would have you take away from this that you should know by Friday, and I will go oh, if you ever make this mistake. So somebody says, hey, I've got this glass fiber or this glass reinforced polymer. That tells you very little. You kind of know the polymer, but is it a thermoset or a thermoplastic? Well, that's important. Is the glass fibers or particles? If it's fibers, how long are the fibers? Are they oriented in the same direction? All this to say, as we start to answer how those questions affect the properties, know that they're all important. Just like if I said, hey, I've got this steel for you. Is it going to work for your component? Well, I don't know. What's its carbon composition? What's its heat treatment? Because all of that are going to affect its yield strength, its modulus, its corrosion resistance. Does it have other stuff in it? Is it stainless or plain carbon? Is it tempered martensite, or do we have spheroidite or coarse pearlite? Very different properties. Same thing with the composites, but we're talking about what's the matrix, what's the reinforcement, but also how is that reinforcement shaped and how is it oriented through the bulk of the material. And ultimately, you're going to want all of that information to say something about the properties of that composite. So why use composite? You look at, so this is a ceramic matrix composite to improve toughness. Okay? And so if we had an unreinforced ceramic here, so this ends up being a little bit weird. The long and the short of it is the properties we get are in between. Okay, so for this particular ceramic reinforcement, it has a fiber reinforcement, and we get some toughness in between them. But you could also look at this and say this was the. We'll see another one, but say this was the ceramic fiber, and this was the polymer matrix. We would get a toughness for the composite somewhere in between here, where the star is. At the end of the day, your properties of your composite are going to be some aggregate of the two. You're not going to get the ductility of the one with all of the strength of the other. But you will get something with different properties than you were able to achieve before. And that's actually a lot of it. That if you look at, so this is, these are called Ashby maps. And it's basically, let's look at two materials' properties that we care about stiffness and density. And each material's class, or even each material, will have some bubble. You know, it'll have a range of modulus and a range of densities for, say, a 1040 steel or polyethylene. And so we'll have, this is the bubble, this green bubble of space occupied by polymers. They have moduli between here, very low gigapascals, so really like 80 megapascals, up to 10 gigapascals. You can get some very high thermosets with high modulus. Here's metals and ceramics, more dense but higher modulus. And what we get with polymer matrix composites is we move into this region here of properties that nothing existed in before. So there are some applications where we want that level of stiffness, but to keep a lot of the low density of a polymer. And until we were able to do composite materials, there was no way to get that. We could only get the stiffness of a pure polymer so high, and we could only get the density of a metal so low. So that's why these carbon fiber, these ceramic reinforced, carbon fiber just happens to be the strongest and the most well-known because of its use in like sports applications and things. But really, a lot of polymers reinforced with ceramics, they've opened up this entire area of combinations of materials properties that are very attractive to engineers. And that's why they're the most well-known composites, why they're used. The other thing we'll do is for metal matrix composites is improve the creep resistance. And this is kind of the general three. So polymer matrix, we're always trying to improve the stiffness. Again, fix the big problem with polymers. And it's that they're not that stiff or strong. Low modulus, low strength compared to the other two. Big problem with ceramics, they're not that tough. The big problem with metals, from an engineering perspective, is sometimes the density, but we're not going to fix that by having a metal as a matrix. So we need to improve the creep resistance of our metal matrix. So we see when we add, we'll take the 6000 series aluminum, a really high strength precipitation hardened aluminum, pretty sure it's precipitation hardened, and we'll add little bits of silicon carbide. And we'll have a higher creep resistance. And so again, this is the chart I was talking about, where if this is a fiber and this is the matrix, so this would be, say, typical of a ceramic or an aramid. This isn't something you need to know, we didn't talk about in class, but Kevlar is a type of fiber that is used as a reinforcement, and it just happens to be a very strong fiber polymer. And then here would be a polymer. And we'll have some combination of the properties. Not quite as strong and stiff as a ceramic, not quite as ductile as a polymer, but we've opened an entire area of properties that are attractive. So again, we talk about the matrix. Okay? We've already talked about all this, but that's there. So the first thing is about the matrix. What is the matrix? This is, again, just talking about the taxonomy of polymers. We're going to say, so an example would be of a taxonomy. This is a specific composite, would be a continuous glass fiber reinforced polyethylene with 10 weight volume percent fibers directionally aligned. It's a mouthful. But by the time we get done with this, you will qualitatively understand what those words mean. You might have to put little word separations between them to think about it all. But okay, the reinforcement could be a fiber or a particle. Those are the first two we're going to talk about. The structural layered. Anybody here a mechanical engineer? So I took a class on composites for more mechanical engineers, and it talked a lot about doing these structural layered composites. I don't know if that's still an offering here because I didn't do my undergraduate work here, but that's a lot more if I think of like honeycomb structures, or take sheets and align them in certain directions. You can get some interesting things there. We'll briefly talk about it. But I basically want you to understand the difference between fiber and particle, and aligned versus discontinuous particle. So we have from a particle reinforcement, so let's start with something simple. We'll get some stiffness, right? So my go-to, so raise your hand like you feel like you have some kind of understanding of a polymer composite reinforced with like carbon fibers or glass or something like that. Am I right? Is that something that you all have some kind of understanding of? It's a little bit stiffer than a polymer sheet, but not like a glass sheet. It's going to be, I know it's not something, who's here like played with one? Or like used a golf club? It's like a carbon fiber.
I have a carbon fiber case.
That's that drum case or trumpet?
Cello case.
You must really love your cello. I don't know that I'd spring for that. I would be like, plastic's good enough. When isn't plastic good enough? When do we start using these carbon fiber stuff? We want lightweight stiffness. Okay, well, for particles, basically if you think of, if we take one phase, the matrix, and add particles of something else, we will get a range of properties based on what the volume percent is. So that's the first thing that's going to, the first thing that's going to affect it. The volume percent of the phase. Okay? So we do that volume fraction of the matrix, volume fraction of the particle. We're starting with the particle because there's nothing to do with the alignment. So we've just got some volume percent of the particle. What we'll have then, based on the rule of mixtures, is an upper bound and a lower bound. Okay? The best modulus we could get would be determined by this equation. And the lowest this would be the lower bound as well, would be, this isn't the way, you end up getting E sub C is EP EM over EM VP plus EP VM. It's on another slide, you don't have to write it down, but we'll basically have an upper bound and a lower bound, okay? Based on how that matrix is distributing the load to the particle. So what's the role of the matrix? It's providing stability, and it's distributing load to the reinforcement. The reinforcement in this case is stronger. It's meant to bear more of that load. But the matrix's job is to get it to the strong particle, so transmitting the load. So we'll have an upper bound and a lower bound, and we'll talk about how that relates to fibers in a minute. But for any particle, we might have somewhere in there, we can't say what the exact modulus is for a particle reinforced polymer, but we can say what is the range it can be in. Does that make sense? It's just based on how is that distributed uniformly, what's the state. There's a lot of things that go on there that in actually manufacturing a particle reinforced composite, we just end up with having a range. There's an upper and a lower, and we're somewhere in between them. So with most of the calculations, that's what you're being asked. What's the upper bound? What's the lower bound? Does that make sense? Any questions? Now, this is also good for electrical and thermal conductivity. You could get a conductive polymer matrix composite if you put a whole bunch of, say, graphite in it. So a high volume percent graphite reinforced polymer composite is going to conduct electricity. Its conductivity is going to be somewhere between that of the polymer, which is not much, and the graphite, which is pretty decent. Not gold, but, you know. So for particles reinforced, we're not going to do this for fibers, but you can use this exact same upper and lower bound rule of mixtures to talk about electrical or thermal conductivity, and there will be a problem on the homework about that. And I suppose it's fair game for the final, right? Okay, so we've seen this idea before with the spheroidite steel. So again, not a composite, but the idea is there, right? Precipitate hardening is kind of like a particle reinforced composite. We do have these with metal matrix composites, where we have a cobalt matrix, very ductile metal, with a bunch of ceramic tungsten carbide particles. And in here we have a very high volume fraction of the particles. We're basically looking for the creep properties of tungsten carbide, but we want some ductility and formability. Some toughness, some formability there. And again, in a tire rubber, we have the rubber matrix with some carbon particles. So another thing we'll put in there. Okay. The other thing I'll say here, this will make more sense in a minute. LF and LC. Length of the fiber is LF. L sub C is the critical length of the fiber. And we'll talk about that more in a minute. Or more on Friday, really. So one of the things I want to... there. Let's just kind of close out talking about this. If I'm loading vertically, which one of these is going to be the strongest? What do you think? Let's go back to our polymer, right? Our kind of a tensile load. Although it would be the same group, yeah. So we go back to our polymer. So let's say this is a carbon or glass fiber reinforced polymer. So it's the fiber that's stiff. Which one of these is going to have the highest modulus? The long continuous fibers, because more of the load is borne by the fiber. Okay. And we'll talk about why the length is important on Friday. But the longer and more directional the fibers are, the higher, you guys, I'm still letting you out a couple minutes early, and I understand you just want to kind of get out, but it makes it hard for people who actually care what I'm saying, which may be a fraction, but to hear what I'm saying. So the discontinuous fibers are going to have less stiffness, and the random distribution will have even less still. But what happens if we load it in the transverse direction? Then which one's the strongest? The random. So with a composite, anytime we're improving the strength by changing something about not the nature of, like the chemical makeup of the matrix and the reinforcement, but if we're changing to a continuous fiber reinforced polymer, we're gaining a lot of strength and stiffness, but at the cost of isotropy. The properties aren't the same in every direction. We have ways of dealing with that, but we'll talk about that more on Friday. So I'll see pretty much all of you at some point today.